Hello, what's up, everyone? I'm Alex Ramey. I'm a member of the Alabama Astrobotics team, and today I'm going to be walking you through a project on how to blink an LED using a Raspberry Pi. The programming language we're going to use is called Rust. It's a new and upcoming language. As you can see over here in the project diagram, we've got the crab here. Its name is Ferris. That's the Rust language's mascot, unofficial mascot. The green box is the Raspberry Pi. We'll be using a GPIO pin today, number 4. GPIO stands for General Purpose Input Output, and we'll be using this as an output pin, which can output either 3.3 volts or 0 volts. We'll be using it to toggle the LED on and off. When we set the voltage to high, 3.3 volts, it will result in current flowing out of the GPIO pin 4 through the LED through this 1000 ohm resistor, which we'll discuss why that was the chosen resistance value, and into this VSS or ground pin, basically a pin provided by the Raspberry Pi that's at ground voltage. Okay, so here's what the project looks like in real life, moving from the project diagram shown on the screen. So on the left here is the Raspberry Pi. This is a Pi 3 Model B. This is what the box looks like. And then on the right here is a breadboard. Breadboards are used basically to prototype electronics. And the only thing you really have to know is that these each of these rows is its own piece of metal. There are no connections between the rows. So like row 22, all 5 of these squares are basically on the same piece of metal, so they're all electrically connected. Row 20 is not electrically connected to row 21 or row 19, however. So the rows are independent. And then on the far left here, these are like power rails. So this far left column is all positive. Typically, we actually have nothing plugged into it. So this is just a piece of metal. And then if you plug, and then this entire second rail here is all one piece of metal, electrically connected. And so the setup we've got here is basically the red wire over here is in the GPIO pin 4 of the Raspberry Pi. And it comes over here and connects to row 1 on the breadboard. This is electrically connected to one of the LED's leads. Current flows through the LED, through this resistor, and then to this ground rail, which is connected by the blue wire back to the Raspberry Pi's ground pin, which is right next to the GPIO pin 4. This resistor is 1000 ohms. You can see the bands are brown, black, red, and then gold. That encodes, basically the brown is 1, black is 0, red is times 100, so that's 1000 ohms, and then the gold band is the 5% tolerance. So yeah, this is the circuit in real life, and when we run the actual Rust code that's on the Raspberry Pi, this is the effect that we get. Boom, so you saw the LED blink. I'll run it one more time. Great, so that is the end state of the project. Okay, so before moving on, I wanted to show a couple of more things real quick. So one is the power supply for the Raspberry Pi. You can see it comes into the board there, and this is the other side of this cable. It just plugs into the wall. So the good thing about this is it outputs 5 volts and 2.5 amps, and Raspberry Pi requires a power supply of 5 volts and at least 1.8 amps. So this is good for that. I also wanted to talk about this LED. So again, this is all unplugged, so it's safe to touch the board now. So this LED, looking at it more carefully, you'll notice that one of the legs is longer than the other. And the reason for this, see if I can show it more clearly. The reason for this is that it's a diode, and so current actually flows through the LED in one specific direction. So the way it's noted which direction to orient this thing is the shorter lead, the shorter leg marks the cathode side, which is the negative side, and the longer lead marks the anode side, which is the positive side. Another way this is shown is if you can look at this vertically, you'll notice that, see if I show, that it's round on the right side, but there's actually a flat edge on the left side. And so that flat edge denotes the cathode, just like the shorter lead denotes the cathode side. Cathode side is the negative side, so we want that close to the ground, and the longer leg's the anode side, which is the positive side. So that's why we orient the LED as such, anode to cathode through the resistor to the ground. Finally, just to touch on why we chose a 1000 ohm resistor. The reason is that the Raspberry Pi pins can only source, are only supposed to source 16 milliamps. And so there's this equation known as Ohm's law of V equals IR. And basically the Raspberry Pi supplies 3.3 volts. We don't want there to be any more output except for 16 milliamps, 16 times 10 to the negative third amps. And then we'll solve for the resistor value. And so this 3.3 is locked in. This is kind of our max current. And because of how this is set up, if we put the max current here, that'll sort of give us our minimum resistance value. So this is really R min. And if you solve this, we get that R min is equal to 206.25 ohms. And so if we choose a bigger value than 206, then that'll just make the current smaller, since the 3.3 is locked in. And so that's all good. And so to be safe, we're using a 1000 ohm resistor. Another cool thing you can do is you can actually check the resistance value of the resistor using a multimeter. And so I've got a cheap one here that I'll show you. But basically this multimeter will display the resistance value if I connect these leads across the resistor. So I should be able to, let's see, touch both sides of the resistor, and it will give us a reading as to how many ohms the resistor is. So we're getting our, my hands are wobbling and stuff, but it's in their neighborhood of 1,000 ohms. So that kind of proves that we read the bands correctly. Okay, so the last piece of this is actually getting the Rust code on the Raspberry Pi that will interface with the GPIO pin and basically make it an output pin and toggle it between being high and low to blink the LED. So on the left here, I pulled up the pinout, basically like the labels for all the pins on the Raspberry Pi. Just so you can see, they're actually not numbered sequentially. These are like the BCM, like Broadcom pin numberings that are used. And so what we're using is actually number 4 and also this ground pin. So in our project, the blue wire is connected to this ground pin going to the breadboard, and the red wire is connected to this GPIO pin number 4. And so yeah, this diagram is basically just how I knew which pin was what on the Raspberry Pi. So to use to access like the UI or the desktop on the Raspberry Pi, there's multiple ways you can do it. You can plug in like a monitor and a keyboard and a mouse to the Raspberry Pi and use it like a normal computer. In this instance, I'm going to just SSH or secure shell into it. But everything I do is going to be equivalent to if you were to use it like a regular computer and open up the terminal application and type in there. Yeah, this assumes that you've got your Raspberry Pi set up with Raspbian installed, the operating system, and like a micro SD card plugged in as the hard disk. And all those the basic setup stuff that you have to do. So in my terminal on the right, I'm on my computer. I'm going to SSH into the Raspberry Pi, which on my network is got the IP address 10.0.0.57, and the username is pi, so it's pi at 10.0.0.57. I figured that out just by plugging a monitor and a keyboard and mouse into the Raspberry Pi, opening a terminal and typing ifconfig, and it showed the IP address. So there might be easier ways to do that. So when I SSH in, I get prompted for a password. I will type Raspberry because that is the default password that I did not change, and we're in. So you can see now that we are the Pi user on the Raspberry Pi host. If I type ls, that will show all of the folders and files in our current directory. Current directory is just this squiggly mark, which is shorthand for like the home directory. And I'm going to use cd, change directory. I made an empty folder called Astro Tutorial that we can do everything in. So there's nothing here. So get rid of that. So I'm in this empty folder, and we need to get some Rust code on here to flip the GPIO pin on and off. So the first thing we have to do is actually install Rust. So I'm using the Rust book. It's the famous book with all the great documentation, and it shows how to install Rust on Linux. So basically we can copy this command to get Rust up, which is a program that will also install Rust. And Rust up you can use later to like update your version of Rust or uninstall Rust if you want. So I'm running this command. I'm going to proceed with the default installation by pressing 1. So yeah, this is installing the Rust compiler, Rust C, which you basically need to compile the Rust program. Rust is similar to like C or C++ in that you can compile the program, and then that executable can be sent around and run elsewhere. So it's a compiled language compiled down to machine code. This is different than languages like Python or JavaScript, where there's an interpreter that's actually interpreting the text file on the fly. So actually you need the source code to run the program. This is not the case. You get a binary executable when you can make a Rust program. Yeah, I guess while this is running, I can talk a little bit more about Rust. It's meant to be used for like super fast applications. There's no garbage collection or expensive memory management, and so it's suitable for like embedded real-time applications. It's a much newer language than C. I think it's about 10 years old. And so the reason Rust is great is it's got a lot of safety enforced by the compiler that saves you from a lot of the traps that programmers can fall into with C or C++. So it's kind of meant just to be a newer language that is still very performant, but that has a better compiler and syntax, or maybe simpler compiler and syntax for reducing the cognitive load of the programmer and making the code more reliable. Okay, so that finished. Let's see what it's saying. It's saying it's installed. Yeah, so talking about path. So yeah, if we were to run like cargo is the package manager for Rust. If we were to run cargo version, we'll get command not found. That's because whenever we run a command, it's basically just looking in all of the directories in our path variable for that program to run. So it couldn't find the cargo program. The reason is if we look at our path variable, echo $path, cargo is not in any of these directories. It actually lets us know that we can configure our current shell by running this file here. And if I actually just print out what's in that file, home/.cargo/env, this is the shell code. It's a bash script. And basically what it does is it adds this .cargo/bin as a prefix to our path variable. So if I were to source this file and then echo our path again, we'll see that the .cargo bin is now at the beginning of our path variable. And now if I run cargo version, it'll actually work and print cargo 1.49. So we are in business there. So the cool thing about Rust, I'm gonna go down this book over here, is we can use cargo to quickly create projects. So in their example, they do a guessing game, but we're going to do an LED thing. So cargo new blink LED. So this, if we change directory into this blink LED folder that was created, we see that there's a cargo.toml file and also a source file. If I go into the source folder, there's a main.rs and the contents, oh my bad, the contents of that file is just a main function that prints hello world. So if I cd .. to go backward up to the blink LED directory and run cargo run, that it'll build the code and then run the resulting executable, we'll see that hello world message printed out. Boom, there it is, hello world. So the real question is, how do we, instead of doing hello world, how do we print, or sorry, how do we mess with the GPIO pins? So there's this library right here. It's actually not the one I wanted to use. One second. Rust GPIO pin. Yeah, this RP PAL is what I wanted to use. So this is a Rust package, and so to add this library to our project, or this dependency, we're going to edit the cargo.toml file. And after this dependency, we're going to add rpal version 0.11.3. This is semantic versioning. So you got the major version, minor version, patch version. You can read more about semantic versioning. They talk about it actually in this Rust book tutorial. They discuss it down here. They add a package called rand, and they talk about some of the shorthand you can do for, specifying the versions that you want and so forth. But anyways, this is going to give us the latest version of RP PAL, which we'll need. So I'm going to write that, and I guess I'll run cargo. Actually, we also need to change our source code to use that package. And so blinking LED is a pretty common thing. And so they've got some example code here that shows how to do it. So I'm just going to take this and paste it into our main function. And we'll step through it in a second. That already had a main function inside of it. So I need to actually get rid of our old main, because yeah, I'm supposed to put a main inside of main. So okay, there we go. So this is I basically just copy and pasted the code on the left into text editor on the right. It's got, including some of the standard library stuff. This is using the actual packages that we just downloaded, the GPIO package. This GPIO LED for us, it's number 4. So yeah, it's number 4, and they're talking about the BCM pin numbering versus like the physical pin numbering. But yeah, we use that pinout diagram to see that the GPIO pin we're plugged into is BCM number 4. So we set this to 4. Then our main function is here. It returns a result type. The OK is nothing, and then the empty is an error. So what this is going to do is going to print a message blinking an LED on and then it'll be the device info, and then it's going to get this mutable pin variable. This is number 4, the variable we just set here, and it's going to make it an output pin. And then it simply sets the pin high, sleeps for 500 milliseconds, sets the pin low, and then returns the OK result. So this seems to be doing what we want. So I should be able to back out here and run cargo run. The first time it'll have to download that dependency, the RP-PAL, so it'll take some time. Okay, I skipped ahead a little bit to when that finished downloading the RP-PAL dependency. So we're just wrapping up 100%. So we got that. It's getting the transitive dependencies and so forth, and now it's building the executable. All right, and it printed the message, and you guys cannot see it, but it's blinking the LED. I'll take a quick video to prove it. Okay, here's the program we just made, blinking the LED. All right. And there you have it. We are blinking an LED with the Raspberry Pi and Rust.